we are Newfound Engineering Group 10, and we're going to be running a presentation today on the design of a hydrokinetic turbine for use in the bay funding. My name is Jackie, this is Brian, Colin, and Brandon. So to start the agenda on what we're going to be covering, we're going to start with project definition, including the project selection, design criteria, constraints, the site assessment, and then we're going to move into our project plan, including our project management, concept selection, and what we're going to do going forward. So before you can implement any design solution, you must first clearly define the problem. So we wanted to focus on renewable energy development within Canada, so we decided to focus on ocean energy generation. There were three different examples which we looked into. First being hydrokinetic turbine, second being a wave energy piston pump, and the third being use of a suction turbine from wave energy. So first, the hydrokinetic turbine, which converts tidal energy into electrical energy using the tides. So the tidal current rotates a vertical or horizontal rotor blade coupled to a generator. The second is a wave energy piston pump, which converts wave energy to electrical energy. Waves move a buoy up and down to drive a crankshaft or pump. And lastly, we have the wave energy suction turbine, which converts wave energy to electrical energy by water moving in and out of the vacuum chamber that forces air through a turbine. So from here, we had to decide where we were going to design our system to be used. Focusing on energy generation in Canada, we decided to go with the Bay of Fundy, located here on the map, due to its high changes in tides throughout the day, which has high energy generation capability.
So we dug into this location a little further, and we actually stumbled upon a very interesting trait, and that's that within this area, Nova Scotia is actually looking to implement more renewable energy sources. And they've set a couple of legal targets. As you can see here on the screen, one is to cut back their fuel consumption by 10%, and second is to convert its energy capacity of 25% renewable by 2015, and then to actually go a little further and go 40% by 2020. Now, this is a little bit drastic because you're actually going to quadruple what they currently have in just 10 years. So in order to do this, they established a force group to construct and operate a tidal turbine test facility in the Bay of Fundy. So we decided as a team then that we could outline clearly our problem statement. And we wanted to act as a company and go in and test a hydrokinetic turbine at this facility to help solve this problem. So just a little bit of characteristics about the Bay of Fundy for those not familiar. It's a narrow funnel-shaped body of water, average annual wind speed 17 kilometers, wave potential 1 to 2 meters, which is relatively low for this type of location. And it actually has the world's highest tide, 16 meters. But why exactly are these tides so high? Well, in order to know this, you got to have a little bit of an understanding of how tides work. So pretty much the sun and moon have a gravitational pull on the Earth, which pulls the water up and down as the Earth rotates. We get 2 high and 2 low tides a day. Our periods are listed here, 12 hours, 26 periods between a high and a high. But the reason that these get so high is because every body of water has a characteristic period. Due to the unique shape, this is roughly the same as the period of oscillation for the tides, which creates resonance in the system. So another key step in any design project is to outline environmental concerns. So we looked at EMF and noise impacts on marine life, effects on microorganisms, negatively buoyant sea ice and how that can affect our subsea equipment, and also any impacts we could have on the surrounding lobster fishery. So once everything was all looked at, we could sit down as a group and clearly outline our objectives and our constraints. So you can see these listed on the board. I'm not going to go down through all of these, but our main ones are to create a reliable, simple design. We want to maximize efficiency, and we want to make our device retrievable. On the bottom, you can just see some constraints that we've set for ourselves.
So now that we have the project set up before us, we wanted to develop a project plan. The first step is to build a Gantt chart. So in our Gantt chart, we've outlined all the different tasks we believe we need to complete between now until the end of the project. each task has a set timeline, and also each task has its own description of all the activities required for that task. We've outlined it on this chart, and so far we are up to date. So, moving straight into concept selection, the first step in designing a turbine is to decide whether we're horizontal or vertical axis turbine. And there are some pros and cons. Looking at the horizontal turbine, it offers certain advantages. It has higher efficiency, it has better startup performance, and there's a much greater knowledge base on horizontal design versus vertical design. Some of the disadvantages, however, is that it must be able to adjust to whatever the current direction is at the time. It's been known to have slightly higher noise emissions, and it can have higher blade costs due to manufacturing tolerances. Looking at the vertical turbine, it is much simpler design where you can have one structure that can take flow from all directions. It also can have situational design versatility in that you can design the blades from the bottom up to vary for, say, a varying current profile or some other features that horizontal turbine cannot. The disadvantage, though, is that it has lower efficiency and it has a rippling effect on the generator output with it has a cyclic power input every time it does a rotation. So, considering our current site, it's a very high power site, very wide, deep basin. The advantages for the vertical turbine don't really apply in this application, so we decided to go with the horizontal turbine for the better efficiency.
As Brian has mentioned, one key feature with a horizontal turbine is that it always has to be pointed in the direction of flow. So in order to ensure that this was the case with the system that we designed, we looked into different yawing mechanisms. There are two different types of yawing mechanisms. One will be an active yawing mechanism, which uses some sort of mechanical drive or electric drive to physically rotate the rotor and nacelle into the current direction. The other would be a passive system, which relied on the natural forces of the ocean current acting on the body of the nacelle through a tail fin or a downstream rotor to rotate it into position using more or less a wind vane effect. When we looked at these three designs, the top yawing system turned out to be a passive system, and it was a tail fin design with a total score of 3.4 out of 5. We came up with three different types of designs. Design number one used this yawing mechanism. It was a tail fin design. It was a conventional hydrofoil, permanent magnet, synchronous generator. It was gravity-based structure, and it would require a speed or pitch controller to ensure that the generator receives the optimum rotational speed. Design number two never used any yawing system at all. Instead, it relied on a bidirectional turbine blade, which would accept flow from either direction. There is some minor losses in efficiency with this type of system. However, it would be mounted with a permanent magnets, variable speed bidirectional generator, have a direct drive system, and it would also have a gravity-based structure. Design number three is very similar to design number two. However, in this case, instead of having a bidirectional blade that takes flow from either direction and switches rotation, it has a bidirectional blade that changes its shape and rotates in a certain way as it goes from base to the tip of the blade, such that no matter what direction the current is flowing, your rotational velocity will always be in the same direction. So then we compiled all these types of designs into a selection matrix. We ranked the overall system as well as the actual generator portion. So when we ranked the overall system, the bidirectional hydrofoil design came in on top, and this was based on design complexity, operational reliability, and industry knowledge, and among some other criteria. We also looked into the different types of generators that would be required for either system, and although the generator for the bidirectional turbine wasn't the optimum case due to the complexity in switching your rotation, and it results in a phase shift in the output of your generator voltage, we determined that due to the simplicity of the overall system and implementing an inverter to convert the phase of our output, that this would be the optimum case for the Bay funding. So we then compiled our results and came up with our preliminary design. As mentioned before, it would be a permanent magnet synchronous generator that relied upon variable speeds, and it would use an inverter to account for the phase shift in the power output. It will be directly coupled to, the blades will be directly coupled to the generator. It has a bidirectional hydrofoil. The nacelle is directly mounted to the tower of the gravity-based structure, and it would utilize 3 to 4 blades to capture the forces implemented from the current.
So, what's our plan going forward? Now that we have a preliminary design, our next steps are to complete the detailed analysis of our environmental data to figure out exactly what the current profile will be. Second, we want to design an efficient set of bidirectional blades. Third, we select the appropriate generator that goes with this design. Fourth, we want to create the structure for mounting the turbine, which will allow for its easy installation and retrieval. And lastly, we want to develop our fabrication and maintenance plans for the turbine. Also, as before planning going forward, we've identified some engineering resource requirements. We want to use SolidWorks to build a model of the turbine and to do structural analysis on the blades. We want to use Flow 3D to help us evaluate its performance, power generation, efficiency. And we were planning to use the tow tank and implement an experiment to get some experimental data for its performance. So thank you all for attending our presentation. Let's open up the floor for any questions.